In this update, I've added multi-GPU support for the Wan Video workflow. Because I recently upgraded my graphics card from an RTX 2070s to an RTX 3090 Ti. My motherboard doesn't have space for two RTX cards, so I used an external GPU dock to load the old RTX 2070s. Then, I connected it via a dedicated PCI X1 splitter card. The OCU link interface provides the maximum transfer bandwidth, allowing me to utilize both of my graphics cards. In the WanVideo workflow, I loaded the text encoder onto the second graphics card, which is CUDA1. The multi-GPU node I used is from Pollock JJ, not Neurotech AI. It supports more types of loaders, including WanVideo. However, I did not load the VAE onto the second graphics card. The reason is that an error occurs when using the WanVideo wrapper solution, meaning that the diffusion and VAE models must be loaded onto the same device. In the native solution, although VAE supports loading to different devices, an error occurs because the RTX 2070s does not support Sage Attention. If both of your graphics cards are from the 30 series or up, you can try loading the VAE onto the second graphics card in the native solution. And in the Flux image generation workflow, I have already loaded the text encoder onto the second graphics card. This is to fully load the Black Forest native Flux dev model into the 3090 Ti's 24GB VRAM. To be safe, you can also load the VAE onto the second graphics card. These past few days, ComfyUI updated the Wan Video wrapper, adding 3 new features. The first is Dilated ControlNet, which can be directly applied to diffusion models. The second is Uni3C, but the official source hasn't open-sourced all its code, and ComfyUI's code is still being updated. We're just previewing it today. The third is ATI, which stands for Anything Trajectory Instruction, used to control camera and object motion trajectories. Let's first take a look at Dilated ControlNet's official demo. This is the familiar ControlNet solution, but it's applied to video. Dilated ControlNet provides 3 control schemes, CANI, Depth, and HED, for 1.3B and 14B text-to-video models respectively. Just place the models in the ControlNet file directory to use them. In my workflow, I've added the Dilated ControlNet module to the text-to-video subworkflow of the wrapper solution. The official source has a recommended value for the stride parameter. Set it to 3 when using the 1.3B model and 4 when using the 14B model. Dilated ControlNet is only for text-to-video models, so its use cases are limited. When using it, just connect the model flow to both the input and output ends. In the Control Video module workflow, I added CANI and HED generation schemes, specifically for use with Dilated ControlNet. Next, I will focus on Uni3C, Unified Precise 3D, Enhanced Camera and Human Motion Control. About a month ago, Uni3C just came out, and I thought it was truly a groundbreaking control method. I never expected to be able to experience it in the WanVideo ecosystem so soon. It has a very good idea, which is to bring video control into 3D space. It creates a 3D point cloud scene based on a reference image, and then places camera animation and 3D human animation within that 3D scene. Then, the process results seen by the new camera are used in the control for WanVideo generation. Uni3C consists of 2 major parts. The first part, the point cloud controller, includes the camera controller. The code has been open-sourced, and ComfyUI integrated it immediately, though it's not a full version yet. Using a reference image, it generates a 3D point cloud and incorporates camera animation. The second part involves generating 3D character animation using SMPLX via Realise-Danced-It. This Realise-Danced-It is the author's another open-source project specifically for controlling character animation. It's used in conjunction within Uni3C. However, the code for the character animation part has not yet been open-sourced. Let's first look at the point cloud and camera control modules. The 3D point cloud scene is rendered according to the camera animation. Parts that are not visible or need to be added are indicated in gray, which can be simply understood as areas needing to be repainted. With the enhancement of 3D data, the results are very precise. Additionally, the camera animation data is encoded by a camera encoder, combined with the latent results for the point cloud scene rendering, and then integrated via this PCD controller into every stage of WanVideo generation control. Theoretically, if there's only point cloud scene rendering without camera parameter encoding, the generated results should not be ideal. However, in the WanVideo wrapper discussion, someone is already controlling camera motion solely using reference videos. Looking at Kajai's code, this segment of camera embedding code is still commented out, with the camera embedding value set to none, meaning camera control is not enabled. However, the camera's movement is indeed influenced by the input video to some extent, which is quite magical. Let's first review Uni3C's camera control, which uses spherical coordinates, including 3 dimensions, radius r, azimuth angle phi, and polar angle theta. This is different from the Cartesian coordinates we commonly use, and it takes some getting used to. We can learn about the results of controlling different dimensional parameters through these demonstrations. The character animation control module uses SMPLX. It can obtain a human's 3D model based on a reference image. The model includes the body, hands, and face. The colors of the SMPLX human body model represent the skin surface's self-relative coordinates based on the scene's environmental coordinate system, with red, green, and blue representing the X, Y, and Z axes respectively. After obtaining the model via SMPLX, Uni3C matches the model to the character by correlating joints in the reference image coordinates and point cloud scene's environmental coordinates. This process is called rigid transformation. It's similar to model matching and skeleton retargeting in 3D software. This completes the setup of the SMPLX and the point cloud scene model, as well as the 3D matching with the character and environment in the reference image. After loading or generating character animation, the camera trajectory images show that black areas represent scene repainting areas, while the SMPLX coordinate color areas for the human body. Not only that, Uni3C also adds a gravity calibration function, which means it can automatically match character animation to the terrain. From this, it's clear that Uni3C essentially integrates and automatically completes all aspects of character modeling, rigging, and animation found in 3D software. Although it's not yet usable, I'm thinking that the scene and character reconstruction process might take a considerable amount of time, but this data can be reused. In subsequent video generation, one would only need to generate character animation, perform gravity calibration, and repaint the video. Expanding further, could it achieve multi-human animation, animal animation, or even prop interaction? Is it possible to save the results of the reconstruction process for other use? Uni3C has opened up a 3D perspective for video generation, full of imaginative possibilities, and is very much anticipated. Once Uni3C's node functionality is more complete, I will add it to my WanVideo workflow. Let's take a look at ATI, any trajectory instruction for controllable video generation. It's about controlling the movement of cameras and objects through trajectories. First, let's look at its examples. ComfyUI has already integrated this tool into the Wan Video wrapper. However, it does not include the trajectory drawing tool provided by ATI. I originally wanted to see if I could get this tool running. However, this tool seems to be based on hand drawing, which is not easy to edit, and the generated trajectory file is in a unique format, which ComfyUI cannot use directly. So, I'm still using the spline editor provided by ComfyUI. In the Video Auto Motion module workflow, I've added a trajectory generation scheme. Note that currently the spline editor only supports drawing a single path. I divided the trajectories into two parts. The first part is the camera motion trajectory, and the second part is the object motion trajectory, with each part supporting 1 to 3 trajectories. When drawing camera trajectories, the starting point should ideally avoid main subjects such as people or animals. In the example you're seeing now, I'm simulating a rightward rotation around a character. The 3 trajectories point to the furthest, distant, and closest points respectively. By controlling the movement direction and distance of the 3 points, the camera's motion process is simulated. This presents a new requirement for us, to be able to imagine the spatial changes brought about by camera movement. The motion trajectory of the main subject is quite intuitive. By using ComfyUI's provided trajectory merging and visualization nodes, you can see the overall motion trajectory. Additionally, I created a node called Save String List to JSON, which can store the merge paths as JSON, serving as motion trajectory presets, so you don't have to regenerate them every time. However, you cannot re-edit the trajectory information in the JSON file. Let's use the Show Text node to see what data is stored here. What's saved are 6 sets of data, each representing 6 trajectories, and each set of data contains the coordinate values for each frame. These are the coordinates for the first frame, these are for the second frame, and so on. According to ComfyUI, 121 frames of ATI are equivalent to 81 frames of WanVideo. However, during my testing, I found a slight difference. The 121 frame trajectory animation seems to finish around the 70th frame in WanVideo. The exact mapping relationship still needs to be tested. In the first frame to video generation workflow, use the load string list from JSON node to read the trajectory data. Using the ATI 14B image-to-video model, disable T-Cache, SLG, and enhance a video. Let's look at the final result. The movement of the camera and character indeed follows the trajectory. Note the hand movements. After the trajectory ends, the hands still move freely along the trajectory direction. This is the frame matching issue I just mentioned. When drawing ATI trajectories, we need to have a relatively accurate prediction of the scale of the scene and the results of camera and subject movements. Otherwise, you will get distorted results. Comparing the two tools, Uni3C has high precision and is more logical, while ATI has low precision and is more intuitive.